All right, let's talk about acceleration. I have three different scenarios. I have constant speed, speeding up, and slowing down. In a constant speed graph, well, in all graphs, all dt graphs, we know that the slope of the dt is the speed, and speed is the rate of change of distance. So if I have constant speed, my slope needs to not change. So it means I'm going to have a nice straight line on my dt graph. On speeding up, I need to get faster and faster, which means that my slope needs to get bigger and bigger. So I'm going to start out flat. Let's try that again. I'm going to start off flat and then get steeper. So it's going to curve. I'm going to have a small slope at the beginning and then a bigger slope at the end. And then for slowing down, I need to start with a big slope and become less. And so curve. So here we've got a small slope. Here we've got a big slope. Here we've got a big slope. Here we've got a small slope. So we're going from slow to fast. That's speeding up, and fast to slow. That's slowing down. So now let's take a look at the VT graph. For constant speed, we're going to be headed in a horizontal line because our speed needs to stay the same no matter what. So this speed is always going to be at like 5 meters per second. If we're speeding up, we're going to start at a small speed and go to a bigger speed. And if we're slowing down, we're going to start at a big speed and go to a smaller speed. So this is really talking about the rate of change of velocity. So what that tells us is that the slope of the VT graph is the acceleration. And that acceleration is the rate of change of speed. Then what I think is interesting is to think about what that slope is telling us. That here, the slope of the VT graph is 0. That tells us that the acceleration is 0 when we're going at constant speed. When we're speeding up, our slope is positive. So the acceleration is positive. And when we're slowing down, our slope is negative. That tells us that our acceleration is negative. All right, so if we're speeding up, we're going to be starting at a speed that we don't know, but is going to be an initial speed. That's what we're going to call it. So whatever speed that is, that's our initial speed. The speed that we end up with is faster. That we're going to call V final. So if we think about what that slope looks like, the rise over run, that's our change in speed divided by our change in time. And that's what our acceleration is. So our equation is V final minus V initial over t, which is really just the slope of our VT graph. So the A stands for acceleration. And we'll come back to the units on that in just a little bit. Our VI stands for the initial speed. Which is the speed you start with. And there's a special case of that rest means V initial is equal to 0. So if you're starting from rest, And v final is equal to the final speed and then watch for stop. So something comes to a stop, v final is going to be equal to 0. Those are hidden givens. They're things that they may not tell you in the problem. T is equal to the time that you're changing speed. And let's talk units. So time is going to be seconds, because that's what we mostly use. And let's change those to a different color. Oops. Oh, I guess I can't. Okay, our v final meters per second. V initial is going to be meters per second. And then acceleration is just kind of weird, because acceleration is going to be the rise over run, which are going to be meters per second, divided by, so that's a rise, and then a run is also going to be seconds. And so that's kind of strange. But then we can write that a different way. So meters per second. We can also write that as meters per second squared. And that's our acceleration units. Meters per second squared is what we typically use.